Now, next we're going to do the mathematics of circular convolution. The math, the notation looks horrendous. Intuitively, really simple. But I firstly wanted to give you that review of how the basics work. Symbol for circular convolution that everybody in the world uses except for Mitra is this. He uses he has an N off on the side. The notation uses modulo operators. Whoops. Which looks just awful. It is going to be of length capital N. So two length N sequence go in, a length N sequence comes out, and you can do this already with no further instruction from me using math. But intuitively, what this means is you're going to graphically convolve X and H normally, and then time domain alias. Remember how when you alias things in the frequency domain, higher frequencies alias low? Same thing here, it's going to get time domain aliasing to make length N. So as an example, if I'm going to take the example we actually just did, and instead of making it 2 long, I'm going to make it 3 long. So here's our regular convolution. And I think you can see it. You'll take h of n and you'll flip it around the 0 point. And you can see that for y of 0, the only parts that will be overlapping will be these two. And then to find y of 1, we'll flip this h of n, shift it to the right by 1, and now these two will be overlapping. So we'll get 2. To find y of 3, flip it around, shift it 3 to the right. Now they'll be perfectly overlapping. And if we shift it to the right 1 more, we'll only get these two overlapping. And then finally, we'll get this one overlapping. And after that, there'll be no overlap at all. So this is our old-fashioned convolution. But to find x of n circularly convolved with h of n, 3 in means we only have room for 3 out. And so this will go down, this will go down, this will go down. Then this will time alias over to the beginning, and this will time alias over to the next one. So we'll have 1 plus 2, and over here we'll have 2 plus 1, and over here we just have the 3. So the results, so the result will be 3 in all locations. And that's how to intuitively find the circular convolution. First find the linear convolution, and then time aliasing. So
and that's because the modulus operation of just n itself
forces it to be within the range of 0 to capital N minus 1. That's right. There's one extra dot, and that's how to compute it using MATLAB. Let me talk about how to do it computationally. I'll be clear how to do it for MATLAB too. It's the DFT of x. And Gordon, how long will that be?
Length of n.
Yes. Times your DFT of h, also length n. And then you're going to take the inverse DFT, which also will be length of n. And it's as simple as that. As an example using MATLAB, we could create vector x like this at the prompt. We could create vector h at the prompt. And then if we did inverse FT, of the FFT of x, we're going to have to dot times this, right, because they're vectors, of the FFT of h, we'll get back 3, 3, 3.